This afternoon, we're going to start with a showcase presentation, Marine Permaculture SeaForestation. We have Ray Schmitt, an emeritus research scholar at Woods Hole. He's a $1 Million X Prize winner and co-founder of both the Neil Brown Ocean Sensors Incorporation and Salient Predictions Incorporation. He has over 40 years of experience in oceanographic theory, observation, and instrument development with Hui, and over 100 publications, 13,000 citations, and 2 patents. So Ray, come on up.
Bring up the slides. Yeah, thank you. Now, I have to confess to a bit of imposter syndrome here. For probably about 20 years, I've been advising the Climate Foundation. Now, what's the Climate Foundation? It's really all due to this fellow, Dr. Brian von Hertzen. He was the son of a Woods Hole scientist. I knew his father pretty well. I didn't know him as a kid. He went off and got a PhD in computer science at Caltech, started his own chip company. I think they were field programmable gate arrays, made a lot of money as a young man, realized he was set for life. But he wanted to do meaningful work with the rest of his life, and he latched onto the website, the name, the Climate Foundation, long before climate was very fashionable. He's very appreciative of the problems we have in oceanography. He loves the ocean. He loves to scuba dive. And so he's started this work on SeaForestation, if you like, marine permaculture. So I'll tell you about that. But I wanted to motivate it a little bit with a little bit of science. The figure here on the left is the pattern of global warming we've seen since, from the 1860s. The last 2 years have been extraordinarily warm. It's ramped up amazingly. The last 10 years have been the 10 warmest years on record in global temperature. On the right-hand side, there's another steeply curving plot, and that's the plot of the vapor pressure of water as a function of temperature. Now, why is this important? A lot of my research is on the global water cycle. This is called the Clausius-Clapeyron relationship, just a function of the properties of the water molecule. And, I put a few temperatures on here from different things. Death Valley can get up to 100, and I put it in Fahrenheit, 130. Phoenix had like a whole month of high temperatures over 119 a few years ago. The Florida Keys got to hot tub temperatures, 100 degrees Fahrenheit. And the global average sea surface temperature had gotten up to 70 C back in 2023 in July. Extraordinarily hot. And we know that most of the heat of global warming has gone into the ocean, over 90%. Why is that those two steep curves so threatening? Well, there's a whole feedback system because of the water vapor response. Water vapor itself is a greenhouse gas, so the more moisture we put in the atmosphere, the stronger the greenhouse effect. The other thing is kind of a new result that's come out in recent research. The water vapor is also very buoyant. H2O is a lot lighter molecule than O2 and N2. And so we have what's called moist convection. And so the stronger the moist convection, the higher it reaches into the atmosphere. And if something goes up, something's got to displace it and come down. So we're bringing down stronger winds in our storms, the stronger tornadoes, stronger derechos, because of this more moist convection because of more evaporation. And the other effect is it tends to concentrate and intensify rainfall into narrower bands. And 30 years ago, we were hoping that more moisture in the atmosphere would cause more cloudiness that would reflect more energy back out into space. That's not happening. It sort of raised the threshold for precipitation. And so we're finding that the rainfall is occurring in more intense and narrower bands. So the intertropical convergence zone is getting narrower. Atmospheric rivers are getting more intense and narrower. And so the subtropics are getting less cloudy, not more cloudy. And that's contributing to the warming as well. So that physical response of the water vapor, vapor pressure, is causing a lot of trouble right now. And I have to say, it's just going to get a lot worse if we continue on this path. So the motivation is we got to get CO2 out of the atmosphere. The ocean has 50 times as much CO2 as the atmosphere. So you could cut the atmospheric concentrations in half by increasing ocean concentration by 0.5%. I mean, that's not a big deal. There are variations between the Atlantic and Pacific in CO2 content. It wouldn't be a real problem for the deep ocean. So it's an important thing to do. How do we do it? Well, there's been this recent National Academy report about doing it. You know, there's things like alkalinity enhancement, liming the ocean, if you like, electrochemical means to do it. Those would both be very energetically costly. The two biological techniques, nutrient fertilization with iron in the high latitude Southern Ocean, will encourage phytoplankton growth. But the other thing is macroalgae. Instead of small phytoplankton, grow seaweed. Seaweed actually is more efficient in sequestering carbon per unit of nitrogen and phosphorus. The phytoplankton are working at the Redfield ratio. This gives you 3 times the boost for every atom of nitrogen. You sequester more carbon. So the Climate Foundation has been pioneering a new method for doing this. And Brian, as I told, he's an entrepreneur, and he likes to generate solutions that have both a self-sustaining economy and also have a climate benefit. So he's been working on, mainly in Indonesia and the Philippines, food security and sustainable livelihoods, hoping to, regenerate ecosystems and work on the carbon balance as well. And the problem we're addressing is this, I guess I already mentioned that the warming of the ocean is increasing its stratification. That's a big problem because the nutrients can't get to the surface to fertilize the photosynthetic, either phytoplankton or macroalgae. So the ocean warming stratification increase is a big problem. And we know that warming has caused big problems. We've lost a lot of the California kelp forest. So Brian's challenge is to try to help restore some of these kelp forests. And he's working with people at Scripps on the California kelp. This is a slide which I haven't fully understood. He provided these slides to me, and as I said, I feel the imposter syndrome. But he claims that algal beds and reefs could be really great at carbon fixation in terms of the tons of CO2 fixed per year. Let's see. Okay. Well, the great thing about working in Southeast Asia is that seaweed is already a food product. And there's a lot of seaweed cultivation there already. So things like permitting and all that were much easier for him to do over there. And because there's a market for seaweed, he could fit right in. But they've had their problems. Depending on the weather, they can have production losses due to diseases, ecosystem degradation, too much nutrients. Some of this stuff gets used for feeding smallhold farmers. So it's an important problem for them in Southeast Asia. So what Brian has developed is a way of cultivating seaweed on lines, kind of in the spokes of a wheel, if you like. Think of a big hula hoop with a lot of lines going to the center mooring point. And the novel thing is we can get nutrients to this system by sinking it at nighttime. So we have this deep cycling system. You take it down at night, down to, say, 100 meters, where it absorbs the nutrients. Bring it up during the day, where it photosynthesizes, generates oxygen, stores carbon into carbohydrates. And so you cycle it up and down. So one of the things I worked with on Brian was how to get the nutrients up to the surface. And we looked at things like salt fountains, which is something I have a lot of expertise in. And I finally convinced them that it was not the way to go. It was too expensive, too complicated. And he tried pumping up the nutrients, but you're pumping up dense water, and it tends to sink. So unless you have an efficient mixing mechanism, it's not very efficient, a lot of wasted energy. He finds that deep cycling like this, cycling the whole structure, is a much more efficient way to get the nutrients and keep the production up. And it doesn't upwell stored carbon, which is one of the problems with ocean pipes. And the really cool thing, it's resilient to the passage of tropical cyclones. So he had a typhoon pass over his project in the Philippines. He kept it down for a couple of days. And that's the kind of cool thing you could avoid ships. And this is the kind of thing that could be automated, with what's it called, the AIS system for tracking ships. You could know if a ship was approaching and get your structures out of the way. He's seeing like a 200% growth increase. There is a carbon benefit because some of the macroalgae sinks. It'll survive a Cat 5 typhoon, and there's millions of hectares of open ocean where this could be implemented. Much of the subtropical gyres, which are very unproductive, if you look at a map of chlorophyll over the ocean, the high latitudes, the upwelling regions are productive, but the subtropical gyres tend to be very clear blue water without a lot of productivity. And this is the kind of thing that would work there. You look at the Sargasso Sea of the North Atlantic, it's not iron limited. There's plenty of iron coming from the dust off the Sahara, but it is nutrient limited. And those nutrients are just on 100 meters, but you can't get them up. Here's some comparisons with a control run that wasn't cycled, and he got plenty of growth increase depending on the time of the year. So he claims that you have the right kind of seaweed. You don't do this with sargassum, which likes to float. You get it with sinking seaweed. Even the smallest pieces will sink 800 to 4,000 meters per day. And of course, a lot of the vegetation is going to contribute to the local ecosystem. As an oceanographer, I've put a lot of things in the ocean over many years, and every time we come back to pick something up, there's a whole ecosystem thriving around the mooring. I know stuff in the ocean that generates a local ecosystem. So he claims that you could get this stuff to sink. Once you get it below 1,000 meters, it's out of the atmospheric carbon cycle for at least 1,000 years. Get it to the bottom of the Pacific, it's probably 3,000 or 4,000 years. So it's the kind of thing we have to do. The ocean's the obvious place to put this carbon. Macroalgae fertilization through a system like these cycling platforms could do it for us. Now, how much would you scale it up? This is what he's been doing. From 2009 to 15, he did some early trials. He's tried different arrays, And the phase 3 trial there with the circle worked out pretty well from 21 to 23. The phase 4 one was a 2,500 square meter array. Right now, he's looking at a 10,000 meter squared array, and that's underway now in 2025. The side benefits, there's a market for seaweed. It's used as food, it's used as cattle feed, it reduces methane emissions. There's a stimulant for agriculture. He calls it big grow. And there's always a fishery that develops around any structure in the ocean. Some of it can be converted to a marine biofuel, if that's the interest, and there are fiber products too. So lots of benefits there. He claims that 20 to 40% of it could be sunk and storing carbon, and so we'd have to see if there's a robust carbon market and you can do the MRV to actually calculate how much you're storing, then you've got something for carbon credits. So this big grow product that they've come out with means that you can do a crop with less fertilizer, and it confers, you're putting organic matter into the soil, and it confers some drought resistance. So the idea is you could do these things offshore. You wouldn't have to do it in nearshore environment. There would be a whole industry of seaweed harvesting and processing, production of this product called big grow, if you like. It's a biostimulant, and they've been selling it to rice farmers because it enhances their productivity. So this is part of it. So this mentions the value chain. There's the big grow. That's a product you can sell. You also have dry pulp for carrageenan and other fruit products. And then you have the carbon sequestration. And he claims that the greenhouse gas impact, that you could be sinking 8,000 tons of CO2 in the deep ocean with a 1 kilometer array of his cycling sequesters. And you'd also avoid 20,000 to 30,000 tons of CO2 emissions, 12,000 tons from avoided fertilizer manufacturing, and 10,000 tons from NO2 nitrate fertilizer application. And Brian has been very effective at putting together international teams of very enthusiastic volunteers in the Philippines and in Indonesia, people who working locally to build these things. There's field work going on to do actual attempt to do some of the measurement and reporting and verification. That's a very challenging problem for all marine storage projects, especially for iron fertilization. But it might be a little bit easier for marine permaculture. And they're working with some underwater gliders, some sediment traps for tracking the carbon flux, using drones to survey it from above. And they're doing the cycling and also doing plankton tows. And, it avoids the hurricanes. And part of this has been funded by $1 million prize from the X-Prize Foundation. It was actually money from Elon Musk. They gave a number of $1 million of awards to people with various CO2 sequestration projects. This was the Climate Foundation was the only one for marine macroalgae back at that. This was a couple of years ago. So I didn't win the prize. Brian won the prize. But so he's, as an entrepreneur, he wants to generate sustainable businesses that can continue to grow seaweed and have the CO2 as a byproduct, but you have, because it's a product that you can sell, you have a viable business to keep going with it, no matter what happens with carbon credits. So some of it has been used to make biochar, which is stored in the soil, carbon in the soil. There's a company called Carbon Wave, used to be C Combinator. He named and co-founded C Combinator. They've recently had a $6 million Series A raise. And SeaForestation was founded a couple years ago. The Climate Foundation provided the ideas, and Brian named it and founded SeaForestation. And they don't have a lot of capital right now, and we're looking for investors. But the thing I like to think of a vision, when I fly over the US, fly over the Midwest, and you see all these crop circles, right? We're pumping up groundwater to fertilize alfalfa and corn with these circular irrigating systems. Why don't we cycle these circular arrays for SeaForestation in the unproductive blue waters of the subtropical gyres, bring up the nutrients, grow the macroalgae, harvest some of it for profit, let some of it sink into the deep ocean to sequester carbon, and it's a system that can avoid hurricanes and shipping interference. And you fly over at night, of course you wouldn't see anything, but during the day you'd look down and you see all these circles, and you'd think, oh boy, we've got a productive ocean instead of a dead ocean. So that's the vision. A way to, you can contact Brian either through me or reach out to the Climate Foundation directly. Brian got trapped in Australia during the pandemic, and he decided to stay there. So he's been there a while. He had a nice big kind of a dorm room, a dorming house in Woods Hole. He contacted us board members in Woods Hole and had us sign the documents to sell it. He's found it much easier to work in Southeast Asia. It's really the only nature-based ocean solution to win a milestone award from the X Prize Foundation for carbon removal. So that's the story. I could try to answer questions, but I'm a physical oceanographer, not a biologist or a chemist. And I just suggest if you really have an interest, you reach out to Brian himself. Thank you very much.